Welcome to Numerical Analysis. Today, we are going to explore a fascinating topic: how to find the rate of change of a function when we do not have a perfect mathematical formula, but only scattered data points. This is a fundamental concept in computational science, allowing computers to understand movement and change in the real world. To understand why we need this, imagine your car's speedometer is broken and you only have a GPS recording your location every 5 seconds. In traditional calculus, the first derivative represents the exact instantaneous rate of change using a continuous formula. However, in real-world computing, we rarely have that luxury. Instead, we deal with discrete data, meaning numerical values recorded at specific separated intervals. To find the derivative, we use finite difference methods. These methods calculate the slope using data points separated by a small horizontal distance called the step size. By making the step size as small as possible, our estimated slope gets closer to the true exact slope. Now that we understand the goal, let us look at the simplest way to calculate this. Conceptually, if we want to know our current rate of change, we can look at where we are now and where we will be one step in the future. This gives us the forward difference approximation. In this formula, f prime of x is the derivative we are trying to find. We take the function value at our next point, f of x plus h, subtract our current value, f of x, and divide by the step size, h. If the step size decreases, our approximation becomes more accurate because the 2 points are closer together. Before we move on, let us see this with a concrete example where we know the exact answer. We want to approximate the first derivative of the function x cubed at the specific point x equals 2 using a step size of 0.1. Using standard calculus, we know the exact perfect slope is exactly 12. We will use this to see how close our numerical approximation gets. For the forward difference method, we need our current point, which is 2, and our forward point, which is 2.1. Continuing with our calculation, we now plug these values into our formula. We calculate the actual function values by cubing the inputs. Cubing 2.1 gives 9.261, and cubing 2 gives 8. We subtract the current value from the forward value in the numerator and divide by our step size of 0.1. The result is 12.61. Since the true answer is 12, our forward method gives us an error of 0.61. This is a decent estimate, but we can do better. Now that we have used this formula, let us understand where it comes from mathematically. To build these approximations, we rely heavily on the Taylor series. The Taylor series is a powerful mathematical tool that allows us to predict the value of a function at a nearby future point if we know everything about the function at our current point. We start by writing out the Taylor series expansion for a point that is exactly one step size forward. In this equation, we have our current value, the first derivative we want to find, and higher order derivatives representing the curvature of the graph. Because our sole goal is to find the first derivative, we need to isolate it. We start by subtracting our current value from both sides of the equation. To finish our derivation, we need to isolate the first derivative completely. Right now, we have the first derivative term almost by itself, but it is still multiplied by the step size h. To completely isolate it, we divide every single term in the entire equation by the step size h. The fraction on the right side becomes our actual forward difference approximation. All the remaining terms at the end represent the truncation error. Truncation error is simply the mathematical garbage left over when we chop off an infinite series to make a practical, usable formula. Because the largest error term is multiplied by h to the first power, we say this approximation has an error of order h. We just saw how to look forward, but we can apply the exact same logic looking backward instead of forward. If we write the Taylor series for a point that is one step size behind our current position, the step size becomes negative. By isolating the first derivative in that backward Taylor series, we create the backward difference approximation. This formula uses the current point and the point immediately behind it in time or space. Just like the forward method, its error is also proportional to the step size, meaning it is an order h approximation. What changes physically here is that we are relying entirely on past data to estimate the present rate of change. Both the forward and backward methods are decent, but they are slightly lopsided because they only look in one direction. We can create a much more balanced and accurate estimate by combining them. If we subtract the backward Taylor series from the forward Taylor series, something magical happens. All the even-powered derivative terms perfectly cancel each other out. This creates the central difference approximation. This method calculates the slope by drawing a line between the point one step ahead and the point one step behind, completely skipping the current point itself. This balanced approach gives us a powerful new equation. In this central difference formula, we subtract the backward point from the forward point. The denominator is 2h because the total distance between the forward point and the backward point is 2 full step sizes. The most amazing part of this method is its truncation error. Because the h terms cancelled out, the largest remaining error term is proportional to h squared. This means if we cut our step size in half, the error drops by a factor of 4. To truly understand why the central difference method is superior, let us look at it visually. Here we see a curve with 3 points marked on the horizontal axis. Our current point x, the backward point x minus h, and the forward point x plus h. The green line is the true tangent, representing the exact derivative. Notice how the red forward line and the blue backward line are clearly tilted away from the true green line. However, the purple central difference line, which connects the outer 2 points, runs almost perfectly parallel to the true tangent. This visual alignment perfectly matches our mathematical proof. Let us return to our previous example to see this massive improvement in action. We are again approximating the derivative of x cubed at x equals 2 with a step size of 0.1. For the central difference method, we need both the forward point, which is 2.1, and the backward point, which is 1.9. We calculate the function values by cubing these inputs. Cubing 2.1 gives 9.261, and cubing 1.9 gives 6.859. Now we plug these forward and backward values into our central difference formula. We subtract the backward value from the forward value in the numerator and divide by double our step size, which is 0.2. The central difference gives us 12.01. Remember, the exact true slope is 12. The error here is only 0.01. By looking at both sides of the point, it provided an answer that is vastly closer to the true slope than the forward method did. Let us look at a real-world scenario where we do not have a mathematical formula at all. A robot's position is being recorded by a laser sensor every 0.5 seconds. We have distance readings at 1 second, 1.5 seconds, and 2 seconds. We need to estimate the robot's exact velocity at exactly 1.5 seconds. In physics, velocity is simply the first derivative of position with respect to time. Because we want the velocity at the middle time point and we have data for both the past and the future, the central difference method is the perfect tool. We can now calculate the final velocity using our sensor readings. We write out the central difference formula, adapting the variables so that p represents position and t represents time. We substitute our specific time values, looking at the position at 2 seconds and subtracting the position at 1 second. We plug in the actual distance measurements of 6.8 and 4.0 and divide by 1. The result is 2.8. In physical terms, this means the robot was traveling at an estimated speed of 2.8 meters per second at that exact moment. We have covered a lot of ground today, so let us review the most important ideas. First derivative approximations allow us to estimate the rate of change of a function using separated data points when we lack a perfect formula. The forward and backward methods use two adjacent points and have an error proportional to the step size. The central difference method is vastly superior because it uses points on either side, drastically reducing the error. By keeping the step size small and choosing the central method, computers can accurately understand change in physics engines, image processing, and machine learning.